Righto, this video is in the probability distribution section. It's a worked example for the normal distribution. And in particular, it's one where we have an unknown mean and standard deviation. Now, some of these problems have an unknown mean, some have an unknown standard deviation. This one's got both, so it's obviously a little bit more difficult. These problems arise essentially because it's an indirect way of testing our understanding of the standard normal distribution. That is a normal distribution with a mean of 0 and a standard deviation of 1. And the correspondence between that and the normal distribution that we're working with some mean and some standard deviation. Okay, so imagine, well, let's have a look at this curve. Here's our sort of standard Gaussian curve. Now, this is generic, really, to any mean and any standard deviation. And the only thing we can sort of glean from it, really, the shape of the curve, are the areas and therefore the probabilities. So whatever you mean in standard deviation, if you, for instance, are up in this top half, you choose a particular point, you would say, well, okay, that is, we've got 10% of the total area and therefore 10% of the probability under that part of the curve. All right, so this horizontal line here, we can put our scale on. I mean, these just come with the standard normal sort of numbers on this one. So I've just used this graphic. The vertical line kind of isn't really a vertical axis as such. It's a measure, but of course this curve actually goes on to infinity to the left. So there isn't really a good place to actually put this vertical axis, possibly in the middle. Anyway. Okay, so the random variable itself is going to vary on what our mean and our standard deviation actually are for the problem that we're working with. We can use our tables or our calculators to actually find to get a correspondence between this value here, this Z value. So Z is basically this letter that we use for the random variable that is normally distributed with a 0 mean and a standard deviation of 1. And let's say, generally speaking, that we're working with a problem that involves a random variable X. Okay, so there is this correspondence, if you like. So for any point on this graph, we can actually we can find the Z value, and there will be an X value that corresponds, and we can switch between the two. And how do we switch between the two? Well, we apply that linear transformation effectively. So our Z value is going to be equal to the value of the random variable minus the mean divided by the standard deviation. So that's how we would switch. And of course, if we're talking about a mean of some random variable X being same as the mean, then clearly this Z value is going to be 0, and so on. So we can see there's that correspondence. So that's fine. What happens, of course, if we don't know the mean and the standard deviation? Well, that's what this problem is about, essentially. So let's have a look at the actual problem and see where it takes us. The heights of a population of women are normally distributed with mean mu and standard deviation sigma. It is known that 30% of the women are taller than 172 and 5% are shorter than 154. Now, this is kind of another sort of form of problem where we've got an underlying relationship, but we have two unknowns, the two unknowns being the mean and the standard deviation. But we have these two boundary conditions here. 30% of the women are taller than 172 and 5% shorter than 154 centimeters. Now, the only difficulty here is that these kind of, well, this is where we have to actually do our conversion. So let's just press on with it. Sketch a diagram to show the distribution of heights represented by this information. Okay, so get normal distribution. So that's where we got this blue line. And then what it's saying is kind of buried on what I've got here, but the values of our random variables, so 154. So here we're putting this 154 here. There's this vertical line here, and this area underneath, I've denoted it by this arrow. This area underneath is 5% of the curve. And then we're saying that 30% of the women are taller than 172. So here's our 172 on this curve here. I mean, don't know. We know it's over here to the right. Don't know exactly where at the moment, but we just put it in here for the sake of argument. So this area here is 30%, and therefore the rest under here is going to be 70%. Okay. Right, so that's the diagram anyway. So we've shown the shape of the curve. We've shown these two particular values and the corresponding probabilities that go with them. So that would be part A. Then he goes on to say, show that mu equals 154 plus 1.6449 sigma. Right, okay. So, well, what do we know? Well, the thing is that when we think about this now as being our standard normal curve, then the random variable value that goes with this 5% is something we can look up. I mean, we can go into our calculator, and if we look at the inverse normal, and we're looking at an area of 0.05, and we're looking up the Z value. So we want a standard deviation of 1 and a mean of 0. And that's going to give us this value here, minus 1.6449 to 4 decimal places. Okay, so that's where that comes from. So that is the Z value that corresponds to 5%. And what we want to do is we want to actually relate that to this 154, these sort of corresponding values. So we're using this little formula here, if you like. So Z, which is minus 1.6449, is going to be equal to the X value, which is 154, minus the mean, we don't know, divided by standard deviation, we don't know. So that's what we've got here. Minus 1.6449 equals 154 minus mu over sigma. We just multiply through by sigma and rearrange, and we're going to get mu is equal to 154 plus 1.6449 times sigma. So that is our part B. All right. So we've applied one of our boundary conditions, if you like. Well, that's okay. One equation, two unknowns. That's not moved us on, but of course we have another boundary condition up here at 172. Obtain a second equation and hence find the value of mu and the value of sigma. Right, so in this case we're going to look up the standard normal random variable value for 70%. Everything obviously works on a basis of less than or equal to. So 70%, and that's going to give us this value here of 0.5244. So using the same process and the same formula, 0.5244 is going to be equal to the X value, which is 172, divided by the mean, subtracting the mean and divide by the standard deviation. Rearrange again, and we're going to get this formula here. Mu equals 172 minus 0.5244 times sigma. Right, okay, so we've got two equations in, two unknowns, simultaneous equations. I've often said it, how often simultaneous equations, I sort of forming them and solving them is such a key component in A-level exam questions. They're usually sort of embedded somewhere in some high tariff questions. And that's exactly what we've got here. All right, so well, basically we are solving these two equations. So we're just going to apply our kind of methods for doing that, and essentially they're going to come out with these two results. Okay, so that's our answer for sigma and mu. And as with the case, in often the case that with these, then we kind of get a bonus for 3. So having done that correctly, we can then go on and use that. Of course, if we haven't actually found sigma and mu, then well, these marks aren't going to be available to us. But fortunately, we know those values, so we can now find the probability that our random variable is going to be greater than 160. Well, which is going to be somewhere around here, isn't it? Somewhere around this point. It's going to be, sorry, no, it's going to be is going to be greater than 160. Yeah, so it's about that point. So we're going to want this area here. That's right. Yeah, so that probability is going to be equal to 1 minus that probability. This probability of x less than 160. We're going to be able to look up on our calculators because we can actually use it to plug in and plug in these actual values when we're looking up the normal distribution, and that's going to give us a value of 0.822. So yeah, you can see it's kind of, you know, all this lot down here, isn't it? Okay, so that is it basically. So essentially what we are doing, we're kind of working back to the standard normal distribution in order to find the z values that these percentages give us. Then we're forming a correspondence, transformation, if you like, between that and that using mu and sigma, and then solving. And so in some situations we might know sigma. I mean, if we'd known sigma here, or the mean mu, then we could have found the other one, couldn't we? But in this problem, we need to find both. That's why we need both boundary conditions. Okay, so hopefully that has been useful. Thanks for listening.